An element is a pure substance made up of only one kind of atom. It can't be broken down into anything chemically simpler.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium.
There are more than 100 elements, each with a name and a symbol. They're all arranged in the periodic table according to their different properties. Understanding how the periodic table works and how it's ordered can help to make chemistry much more logical.
It turns out that these building blocks, not every one plugs into every one. So you can't just combine a random set of things together and have it stick together. But there's a certain set of rules about how they combine. And the rules are embodied in the periodic table. Each one of these little building blocks has on it, I think of them as sort of arms that reach out. A certain number of arms that reach out. And they try to hold on to other arms on other ones. And they're only kind of happy if all of the arms are holding on to something. So for example, hydrogen has one arm sticking out, and oxygen has two arms sticking out. And so if an oxygen molecule holds onto a hydrogen molecule in each arm, then they're all sort of happy because the hydrogen molecule has one arm to hold onto, and the oxygen molecule has two arms to hold onto, and the other hydrogen has one. And that happy combination is called water. It's two hydrogens and an oxygen, H2O. That periodic table is, to me, one of the wonders of the world because it's a sort of system that explains an awful lot about what goes together and what doesn't go together.
The periodic table contains all known elements and it's organized in groups and periods. The groups run vertically and the periods run horizontally.
The elements are special because everyone is made from a different kind of atom, just that one kind of atom. Every element has its own special properties. But sometimes those properties are shared by a family of elements. The periodic table groups these families together. The horizontal rows of elements are called periods. The elements along one seem quite different, but look up and down a group of elements and they seem to be quite similar. Understand the characteristics of a group and you get a handle on the behavior of all the elements in that group. Here's lithium, a soft grey metal. Below it is sodium, softer still. Like all the elements in group 1, they share similar properties. Across the whole periodic table, a picture emerges which can reveal hidden secrets in nature.
When you're thinking about the periodic table, try to look for patterns in the way it's laid out, especially relating to the electronic arrangements of the elements. Let's go back to the group mentioned in the clip. The group 1 metals, or alkali metals as they're also known. Lithium, sodium, potassium, rubidium, cesium. Pause the tape and copy them down into a table. Now watch the following clip and see if you can fill out the table showing how they react with water.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
How did you get on? Your table should look something like this. Lithium floats and fizzes and gives off hydrogen. Sodium moves quickly across the water, fizzes and gives off hydrogen. Potassium sets alight with a lilac flame. Rubidium produces many sparks immediately on contact, and finally cesium explodes and in this case shattered the glass container. You'll notice that the reactivity increases as you move down the group from lithium to cesium. Group 8. The noble gases are another part of the periodic table you'll really need to know about. The group is made up of helium, neon, argon, krypton and xenon. Here's a quick introduction to the noble gases.
Take the noble gases. There's not much chemistry to see, but there are changes in their physical properties, for instance in their density. The noble gases are xenon, krypton, argon, neon and helium. A balloon filled with helium rises quickly. A neon-filled balloon rises slowly. An argon balloon falls slowly. Krypton is denser still, and xenon is the densest of all.
The noble gases are highly unreactive. This is because their outer energy levels have the full quota of electrons.